Are we good to go? All right. Hello, everybody. I'm Björn Fahller. I'm here to talk to you about higher order functions for ordinary C++ developers. A little bit of background. I live and work in Stockholm, in Sweden. Spent most of my career developing embedded software for communications devices of various kinds. I wanted to do a talk about higher order functions for some time because they aren't used by C++ developers much. There's really good historical reasons for that. It's not been convenient to do so for a long time. Before I get going, though, I just have to tell you a little short story about my trip here that's pertaining to my choice of T-shirt today. As I was on board the plane from Stockholm, we were pushed out from the gate and started taxiing. After a few minutes of taxiing, the plane stopped and we stood still for several minutes. The captain announced that, yeah, we have some malfunction indication here, but we've been communicating with the technicians and they say it should probably be okay if we reboot the system. And after another 5 minutes or so, the captain announced, yeah, it's all green now, so we're good to go. So that feels great. But I wasn't more than 10, 15 minutes late here to Oslo, so everything worked out. So yeah, trust me, I'm a programmer. Higher order functions. What is higher order functions? This is a little bit of what I'm going to talk about today. Very, very, very brief introduction, and then I'm going to sort of explaining by doing, gradually expanding an example. And by the way, I do want you to interrupt me, ask questions, come with reflections, throw things, maybe not throw things, but whatever, so we can get a communication going. After this expanding example, I'm going to introduce you to OptionalT, which is a cool thing, and an extension of it that makes it even cooler, and then working with overloads, which can actually be a little bit tricky in C++. So, without further ado, a higher order function. This is the definition. You can find it in many places. A higher order function is a function that takes other functions as arguments or returns a function as a result. I copied and pasted this from the Haskell documentation, so it should have some homeopathic memory of extra truth to it, so let that sink in for a while. So, have any of you used higher order functions from this definition? Yeah, okay, most of you, not everybody. Have you written them? A few? Cool. Can you come up and do the talk for me instead? For the purpose of the context of this talk, when I say a function, I mean anything that can be called. It doesn't have to be a function in the C sense of a function. It can be a lambda, it can be an object with a function call operator defined. Or it can be a static member function or what have you, something that can be called. So here's an example. It's the none of, one of many higher order functions in the standard library. So we say if none of the values in the vector v are equal to 0, then something. So we call none of with the lambda that is a function. So none of is a higher order function. It takes a function as an argument. Those of you who haven't written any higher order functions before, ever, here's a typical implementation. Normally it makes very little sense to implement none of because the standard library does it. But if you were to implement it, this is how you do it. They're often, very often, templates. So this one is a template that takes iterator types and a predicate. And you have the classic loop over the range. And if the predicate is true, then obviously at least one of the values in the range is true, so none of it is false, so we return false in that case. And if we exhaust the entire range without the predicate triggering, then it is true. None of them were true. So that is really how you write it. You can be extremely fancy if you want to, if you really want to show how enormously good you are with Svinai trickery and whatever, but the standard library doesn't. So generally speaking, don't bother. So it's not really very complicated. So we can use this. So we have some other, the program expands, we call another higher order functions to any of. So while any of the values in the range equals num, then go on, keep looping. And I find this code extremely annoying. Any ideas what is so annoying with this code? It's in boldface. The two lambdas are the same, more or less. It's the same lambda, again, twice. I hate that. Also, even though this is not, these are not very complicated lambdas, you understand what these means, but you have to read them to understand what they do. So I want to do something about that. So let's remove the clutter. What can we do to give this a name instead, to express intent? Well, I can make it a function. C++14 gave us the auto return type, which makes it easy to return lambdas. And by doing that, we can capture the intent in something that we say, we call this function equals with a number. We return a lambda using the auto return type that captures this number that we gave and returns true if, when called, the value equals the number we gave. And at this point, someone usually asks, what about std function? Couldn't we do that? And yeah, we can. There are problems with function. At this level, it's not really problematic, unless you're really find performance to be important to you, because std function has quite some overhead. But there is a conceptual problem also that we'll get to very soon, because obviously you don't want your higher order function in this case to be specialized for ints only. You want to be able to match anything. So I want to say equals whatever something that can be quality compared. And C++14 also gave us the auto in the parameter list for lambdas, so generalized lambdas. So now it's not even important that the value we gave as an argument to equals, which is a t, is the value that the lambda is then called with. What's important is that they are equality comparable. So say, for example, that we call it with a std string. The lambda can be called with a const char star. And sure, I can sort of do that with std function. But this is not exactly the same, is it? Because now we say that this std function that is returned must be called with the same type. For example, a std string. So in the case I call equals with std string and call the lambda with the const char star, I get a temporary created and destroyed for every call. That is expensive. But turn it another way, the other way around. I call equals with a const char star and want to call it with a std string, then it doesn't compile. Because a std string cannot be implicitly converted to a const char star, so we get an error. So these are not equal. These are not the same things. So std function is good for many things, but There is a cost to it. There are limitations to it. So these are not the same thing. The one below that uses auto return type is more generic. Yeah, so there we have exactly what I just said. So back to this, and now we can write the code like this instead. So say, if none of the values in the vector equals 0, then. And while any of the values equals num, then. This is more expressive code. It communicates intent. People laugh when I say this, but this enables us to have an argument over names. That is actually a good thing. Because when we are having an argument over the name of something, we are actually building a mental model of what is actually the problem, what is the intent, what do we want to do. I could have called this foo, but it would have been meaningless. It wouldn't have helped us understand what the code means. But by giving it a name that conveys intent, we can read the code and get the idea of what it is meant to be. And if there is a bug in here, we can argue quite easily is it the intent that is wrong? Shouldn't it be equal? Should it be something else? Or is it actually a bug in equals implementation? It says it does equality, but it doesn't. So by giving it a descriptive name, we can pinpoint where the problem is, instead of just reading the lambda that says what it does, but it doesn't say what is it meant to do. When it comes to naming of higher order functions, I prefer, you will see this a lot, prefer to give them names that read well in the context they are used. I think this is reasonably successful anyway. Are you familiar with Matt Godbol's Compiler Explorer? If not, you should be. Absolutely should be. Let's have a look. People, especially from my background in the embedded world, think, oh no, we cannot do this. The overhead of this abstraction, this is too expensive. So let's have a look. Do you recognize this code? We have, yeah, I wrote any of and not the other one, but regardless. We have an equals, prepared it for std function and the simple one, and some function that just checks for a match. So what do we see here? We get RAX and RCX are obviously the begin and end iterators. We compare them for equality. If they are equal, we done and return false. Otherwise, we compare whatever the iterator points to with a value given, the int here. If they are equal, we jump here where we return true. All right, cool. Otherwise, add 4, because that is the size of an integer on this platform, to the iterator and go another revolution. I would claim that this is about as efficient as it gets. There's no overhead in here. We can make an experiment. Let's not call my any of, let's call std any of. Wow, look at all this code. Maybe my colleagues are right, there is a tremendous overhead in this. What are we seeing here? Any ideas? Why does std any of generate so much code when this trivial one doesn't?
Debugging machinery?
Pardon?
Debugging machinery?
No, not debugging. I have no debugging on. I'm using -03 here. I can lower that a bit, but that is not the case. No. It actually does a partial loop unroll. So the implementation of std_any_of does compile time reflection and sees, wait a minute, we are looping over a vector where all elements are adjacent in memory. I can do a partial loop unroll, so it actually does 4 comparisons per revolution, which makes it execute a lot faster, because we have fewer branches, we have better locality of reference. So that's why we get a code size bloat, but we get better performance. So maybe if you're writing code for a microcontroller where you have like 128 bytes of program memory, you may want to use this naive own implementation instead of the standard one. But if the space for your binary isn't important, then absolutely use the standard version instead of writing your own, because why write something that is already given to you and is well documented and is well debugged? But for the sake of completeness, let's have a look at using std function instead. Wait a minute, before we do that. A quick count, 19 instructions all in all. Std function is meant to be usable across a binary interface, so an ABI. So say in an API to a shared library, where then you cannot just pass something that is compile time information. Everything needs to be known explicitly. Exactly as it is. So std function is well defined exactly how it is laid out in memory, and all the interesting bits are anonymized out. You cannot see them, but this also means that there is an overhead. The compiler cannot see through it. When we just return the lambda, the compiler sees through everything and sees what it can remove. So std function is great for what it's meant to be used for, but it can be expensive. Yes?
How does it behave with no RTTI? Because there seems to be awful lot.
Yeah, we can do that. Not a whole lot better. We can also do okay. And it got a little bit better too, but still not.
The code bloat is due to the type erasure.
Yes, if you didn't hear, it's a type erasure that causes the cost. But of course, if you need to pass a function into a DLL, then std function is the way to go, obviously. But just understand that std function is great, but it has a cost. And sometimes the cost doesn't matter, so why bother? But sometimes it does matter. Right. Questions so far before I go on? Yes?
Do you have any comparisons of bigger projects, how much the code load is overall, when using these functions compared to using the hand-roll version? Because code size is bigger in the end, right? When I use like NUF or
No, the code size is not bigger when you use the standard library functions. No.
compared to hand-roll, so you do your own for loop.
Yeah. When you roll your own for loop, you get the same code but with more bugs.
Okay.
Yeah. I mean, seriously, look. Can you do better with a handwritten loop than this? Can you? No, you can't.
What we see a lot of template code, max code.
Yeah, yes, the observation was that a lot of template code generates code bloat, and that is true. But from that draw the conclusion that all template code generates code bloat is false. Yeah, so here, no, this type of use is for free. There is a cost in compile time. It's not tremendous, but it is measurable. But in your generated binary, no, it's not there. All right. So we got through this extremely brief example. So let's expand. Let's do things. Like I said, I work for Net Insight. We make networking equipment. I write software for said networking equipment. In networking equipment, we deal with IP addresses. So I write a class, IP address. We can create it from 4 bytes because it makes test code easier, and we can create it from just a 32-bit number. We have equality comparison operation. If you're wondering why I have an address type instead of just using 32-bit integers, come to my talk tomorrow about type safety. We need a net mask that makes sense. A net mask is sort of an IP address, and I want to be able to do, well, masking of IP addresses and net masks to get a masked address. And with this, an absolutely obvious higher order function is IP matches. A function that I give an IP address that I want to look for and a mask. And I'm using the auto return type to return a lambda that captures the thing I'm looking for in the mask, and it's callable with an IP address, and we check if the masked desired IP address is the same as the masked address called with. And if there's only one thing I want you to remember from this entire session, it's this: use auto return type to return lambdas. If you don't remember anything else of what I'm talking about this entire hour, then I'm happy, if you do remember this one. So with this higher order function, we can write, for example, remove if we have this vector of IP addresses, remove if v.begin, v.end, IP matches the 192.168 subnetwork. This is cool. This is readable code. And of course, in networking equipment, we also use IP interfaces. And an IP interface has a state. It can be on or off. This is obviously simplified beyond reason, but bear with me. Making the example completely realistic does not make for better slides. So we can set the state, which involves talking to the IP stack, maybe talking to hardware. We can query the state, which can be done inline because we can just cache it as a member variable. And then we have other functions also to get its address, get its net mask, get its default gateway, and a bunch of other interesting or not interesting stuff. And now comes a question. If I want to, say, search for an IP interface that has a certain address, how can I do that? I want to use this IP matches predicate that you saw on the previous slides with an IP interface. So I need some way to extract the address from the interface and feed that into the IP matches predicate. So I would like something like, if I have a function f1 that takes a y and returns a z, and I have a function f2 that takes an x and returns a y, then I want to be able to compose them as one function that takes an x and returns a z by calling f1 with the result of calling f2 with x. So for example, if I have f2 being a select address function that takes an IP interface and returns an address, and I have the IP matches higher function that you saw earlier, then we can see that the result of composing those would be something that is called with an IP interface called select address, gives us an IP address, sends that IP address into IP matches, which gives us a bool. So how can we write such a composition? and it's surprisingly easy. So I just write a function template that takes two functions, f1 and f2. Use the auto return type, return a lambda, that when called with something x, it returns the result of calling f1 with the result of f2 of x. And we're done. So then I can use this. Say, with a vector of IP interfaces, find if interfaces.begin, interfaces.end, the composition of IP matches 192.168.1.1 and select address. But of course, yeah, select address is an obvious function, just perfectly ordinary freestanding function. But of course, this composition can maybe be used in several places, so why not moving it out? Write a new function, address matches, that takes an IP address and a net mask and returns this composition using the auto return type, and then we can use this address matches function instead. Find if interfaces begin, interfaces end, address matches 192.168.1.1. Cool, I think. And then, of course, we add the other necessary functions, select gateway, select state, select mask, or what have you. So I'm now sort of venturing into the realm of insanity here. Bear with me, there is a purpose for it. The code will become a little bit crazy. So, okay, find if, this is not too insane, I think. Find if with when all, so we want to match several predicates here. Address matches 192.168 subnetwork, and the state is off. So how do we do this? Another higher order function. Here I'm using C++ 17. Are you used to C++ 17 fold expressions? 3 hands, 2.5. Okay. I'll walk you through it. What this fold expression here means is that the P is the predicate. It just sort of introduces the beginning of something. So we say, I want this expression to be piece of X expanded over all the P's, in this case with logical AND. So in this case, this call, P's will be both address matches and state is. And it will expand to first call piece of X, or rather, piece of X will be address matches 102.168 subnetwork. Logical AND with the rest state is off. And if I had called with even more predicates, they would be just more logical ANDs of the application of each of them. And you get the normal logic short circuiting. So if the first predicate is false, then the rest of them aren't called even. You can do this in C++ 14.2 with a hairy recursion. You really don't want to go there, but you can. Where you just call, you have one where you have at least one predicate, and you return the application of the first one, logical AND with the rest of them. And then you have the base case, where you have nothing, then it's true. So this works, but it's a bit unpleasant. And if you're an experienced template library writer, you know about even more horrible shortcuts to make it look more like the fold expression version, but I'm not going to show you that because that's a whole different kind of talk. That would actually be a whole talk on its own. All right. So address matches you saw before. State is of course another composition. compose of equals of the desired state with the function SelectState. So there is a recurring theme here, isn't it? You use the auto-return type to return compositions or naked lambdas. And you just build things from there, just combining more and more stuff. So now we're going full-blown crazy. So we're walking through all IP interfaces, and we say, if all of address matches in status of is true, then set the state on. So how is an if-then implemented? I think you can write it. Again, a template that takes a predicate and an action. If the predicate is true, call the action. In this case, I've decided more or less whimsically to do a perfect forwarding on the action, because why not? You get the idea. It's the same. And SetState is, of course, also, again, use auto-return type, return a lambda that captures the state we want to set. And when called with an IP interface, we call the member function SetState. So nothing weird. You understand this code? Cool. So time for some live demo again. How expensive is this? Okay, so you recognize this code. We have our equals, we have an IP address, net mask. Yeah, I did a renaming and I forgot. Okay, sorry. That is IP matches. We have the IP interface, select address, compose, select state, set state, address matches composition, state is composition, when all. Look, Andreas, I remember to change it to C++17. Thank you for that. A handwritten for each, because I don't want to deal with this partial loop unrolling, making the result more difficult to read. And we have a function that does it all. So this code is obviously bigger. We need to save state on the stack. We don't have enough registers. But we can check. We get RBX and RBP to be our begin and end. Check if they are equal, then we're done. Jump to 5 here. We'll just leave. If they're not equal, we get a value from offset 0 in the IP interface, which happens to be the address. XOR with the address we're looking for, and mask off the lower bits. If it's 0, then it was a match. If it wasn't, we go on. But if it was a match, then we check offset 12, which happens to be the mirror of the state. So we check if it's 0. If it is, we call SetState with a 1. Otherwise, add 16, because that is a state, the size of the IP interface. See if we have reached the end. If not, another revolution. There's absolutely no overhead in here at all. Everything disappeared. The compilers today are magic. Absolutely magical. Actually, I believe it became even smaller if I use -OS. Yeah, a little bit. Tiny little bit smaller. I haven't benchmarked them to compare if any of them are faster, but yeah. So don't be afraid to use these constructions because of a fear of cost. At least not in terms of the generated code. It's not expensive. Questions? Just stunned completely. All right. So you're asking too few questions. I'm going to finish early. So we've seen this brief intro and the gradually expanding example. I'm not going to expand on that much more, a tiny bit maybe. OptionalT. OptionalT is kind of cool. Are you familiar with OptionalT? It's part of C++ 17 standard library. The intention of OptionalT is to say that an instance of OptionalT is something that may have a T, whatever T is, or it may have nothing. Like I said, it's in the standard library of C++17. It is available in a number of open source libraries for at least C++11. I don't know, maybe older, but definitely from C++11. It's extremely useful in lookup functions to say, for example, in a route lookup, give me the gateway node for this IP address, and it says, yeah, you should go to this address, or say, I don't know, never seen this, I have no idea where you should go, or some other lookup function. So it's a way of saying, here is the value, or sorry, I could not give you a value. Super useful. In the standard library, T must not be a reference type, which is not a big problem, but it's a bit annoying. The reason for reference types not being allowed is that it's not obvious what assignment means. If you have an optional T reference that does refer to something and I assign to it, what does that mean? Does it mean I'm assigning to the thing that my optional refers to? Or do I mean that I'm rebinding the reference to something else? So to err on the safe side, the standardization committee decided to say that, let's not support it. There is this odd thing called std reference wrapper that you can use instead. It's not that big of a problem, a little bit annoying, but hey. So, we can do this. I can use a lookup function, a higher order function that takes a predicate and searches for IP interfaces to search for the first one. Actually, it should be lookup first or find first or something. That matches a predicate. So the way to use is, the use I prefer at least, is to, I start by creating an instance of the optional that is default constructed, that is, it doesn't refer to anything, so this is the false state. And then if I can give it a value, I give it one. This is very friendly for return value optimization if you're into, if you find performance to be important, and it means you're not forgetting any cases. So in this case, I used std find if, and if it's not the end iterator, then I give a value to my return value. That is, my std optional becomes now defined to have a value and return it. So a use case can be something like this. I look up an IP interface with some predicate, and if it is found, then I can do stuff with it. So this is kind of neat, but not very much in the style of higher order functions, which I think I sort of meant to talk about now. So enter this fella. Simon Brand, taught on Llama on various social networks, all-around nice guy. He's written his own optional that is available on this GitHub link. It works for C++11 and up. And it does support using references. But more importantly, it does have some functional style extensions that I'm going to just briefly introduce you to. And if you're curious, there is a standards proposal for using this. I think this was, or at least was intended to be discussed at the standardization meeting in Rapperswil in Switzerland last week, but I don't know if it actually was. What this thing does is, it's under the TL directory, TL optional, TL for Tartan Llama. If you ask him why Tartan Llama, he just says he was once a teenager, and that's it. So I create an optional V that a default constructed, so it doesn't have anything. Then I assign to it, so now V refers to I. And if I say v.value equals something, then I'm actually assigning to the thing that v refers to. But if I have a new variable j and I say v equals j, then I'm rebinding the optional to refer to j instead of to I. So I continues to be 4. This is not super exciting. Now comes the exciting bit. It has continuations. So you can say, and then. And then is only callable when v has a value. If v doesn't have a value when you call and then it does nothing. Nothing at all. Whatever and then is called with must return also an optional. So you can chain them more and more and more. You also have .or else. Or else is only called if v doesn't have a value. And or else can be a void function, which means it continues to be uninitialized. But it can also return an optional. So we can, for example, use a lookup and say, or else create. That is cool. And more than that, you can also just concatenate them chain them as member function calls one after another. So this is neat. And now we can write code in a much more pleasant style. So instead of doing this, where I'm having this if statement to decide whether I want to do something or not, I can say, look up this and then do stuff. The disadvantage is that the do stuff must now return an optional, but that is a very small price to pay for this convenience. So for example, I can say, look up this address and then set the state. Or I could use a lookup or create. Or I can chain them and just say, look this up and then set the state, or else just say that it failed. And this or else will be called if lookup fails, or if lookup was successful and set state failed. This is neat. I want to see this in one form or another standardized. I forgot to say that Simon's implementation that I gave you the GitHub link to is explicitly placed under public domain, so no strings attached. So let's have a look. How expensive is it to use this? We have all this stuff again, using TL optional here. You have all this stuff. Yeah, I changed, as you see here, the SetState member function now returns another optional, so that it can say that it returns a reference to itself if it is successful, or it returns an optional that does not own a value if it failed. So you can use these to chain them. So I have my lookup function as earlier, and then we can see lookup interfaces, address matches, and then call SetState, or else just print an error message in this case. And this is not super difficult. Again, the iterators, see if we're done. Yeah, the compiler is clever. This is the IP address. Loop until we find something. Check if we have a value. If not, go to print the error message. Otherwise, call this SetState. Check the return value. If it was now false, go to print an error message. Otherwise, we're done. No overhead. This is so cool. Well, actually, there is 1 byte overhead because in terms of storage, because the optional type has a Boolean that says if it contains a value or not. But you trust me, you can pay that overhead. And now we get to the facepalm part of this talk, working with overloads, because overloads are great, and they are a pain in C++, at least in this context. So if I have an IP interface as before, and I have this function select address, and I have something that works with it, everything is fine, no problem. But then somewhere in my program, I also have a customer that has a street address that I want to be able to query, so I have a function select address that takes a customer. And this is what MSVC says if you try to call it. It's the transform no matching overload function found. Could not deduce template argument for FN1. It's not very friendly, actually. At least it's not a spew of page after page of problems, but it's not very friendly. Everybody knows clang is the king of good compiler error messages. Or not, in this case. It's not very friendly. The reason this is a problem is that we're saying call transform with select address, but there are 2 select addresses. And overload resolution doesn't take place until inside the body of the transform, when it is called with whatever the iterators refer to. And then it's too late. So at this call site to the transform, it says transform to which select address exactly? I cannot know. Sorry. And it's not very good at saying what the problem is, unfortunately. So how do we deal with this? I have 2.5 solutions, roughly, depending on how you see it. So solution number 1, I've prepared for some really, really, really hairy C++ stuff. Why bother? I can honestly say that I have not had this problem in my code, ever. I had to construct an example just to be able to show it to you. So why bother? Arrange your code such that, I mean, in this case, where you have a customer with street address and you have IP interfaces with IP addresses, these are completely different domains of your code. This is only a problem if you have one source file that needs to see both at the same time, and that probably won't happen. So it's rarely a problem. So, yeah. But if you actually do need it, we can go to solution number 2. Call it through a lambda. Because a lambda is one thing that is callable. In this case, I'm using the auto function parameter, so it's callable with anything. And then inside that call, it knows which of the select addresses to call. And that is okay, because the lambda is one thing. That one thing is sent into transform. So it works. So I think this is okay occasionally. It becomes cumbersome if you need it often because you need to read this lambda. So you have the 2B solution, and this is the one where purists need to look away. Sorry. We enter the dreadful macro. So I have a macro lift that takes a function and does just the same thing that you saw earlier. But now on the site of the call, you just see the transform begin and back inserter lift select address. It's easy to read. Of course, if you want to do lift the right way, you need to do that. Oh boy. Have you seen Vittorio Romeo's short talk, you must type it 3 times? That is horrible, but that's the way it is. But on the other hand, by putting that stuff in a macro, you write it once and you use it many times. And really, that's it. Of course, macros are evil. They are, but what can you do? Let's hope for some evolution in the language that makes us able to express such things without lambdas, but without macros, but we're not there yet. Okay, just briefly show you that this is really nothing. So we have a compilation error here. The reason is that I'm actually using this example where I set the state, but I changed things such that I added a customer with its select address, which means that this compose fails because it doesn't know which select address to call. So let's do that. And the result is the same code as we saw before. So it's not expensive to do this. All right? Yes?
How about namespaces?
Namespaces and macros. Yeah, like I said, macros are evil. They're problematic. Yeah. Then I would say you return to handwrite your lambda. There are other techniques that are more elaborate, but I don't want to go there. Yeah.
It looks horrible. What about explicitly instantiating the template? By defining the types there, not doing the compiling, then you can force automatic overload. I mean, of course, it looks terrible, but
Yeah, it's difficult to do when one of the template parameter types is a lambda type, because what is that? You can, yeah, I guess you didn't hear. The suggestion was, or the question was, what if I am explicitly instantiating the lambda with the types I need? And that becomes difficult if the type you need is the type of lambda. You can do it with decal type, but it's not a lot better, I think. Yeah. Other questions? No? All right. So that was pretty much it. So let's just summarize a little bit here. When I wrote an earlier version of this presentation, I discovered, I had actually not thought about this, but I discovered that these functions sort of belong in different categories. So we have our domain-specific ones on the right, the IP matches, select address, etc. And we have the domain-specific composed functions like state is and address matches. But then we have a bunch of functions that are completely generic. They have nothing to do with our problem domain. So they really belong in a library. So I scouted the internet briefly. I didn't make a very strong effort, but briefly to search for some cool libraries to use. And to my surprise, I actually didn't find any. So I wrote one. Although you're free to use this if you want to. It's under Boost license. Although I went a little bit crazy there with C++ 17 through and through, and it's fully const export, it's fully SFINAE friendly, it's perfect forwarding everywhere, and it is a compiler bug magnet. I filed 4 compiler bug reports so far on Compose alone. And that's only because I haven't even tried it with Microsoft's compilers. So feel free to use it if you want to, but you have been warned. But it is more generic. You can call all functions with any number of arguments, etc. So, yeah. And I try to give good compilation error messages with static asserts and such. But that was then, when I wrote this. 2 months ago, almost to the day, Boost 1.67.0 was released, and it has Boost Hoff higher order functions. I haven't used it because I actually only learned about this last week. I haven't even written a hello world with it, but I've briefly glanced through the documentation, and to my surprise, there is very little overlap between this library and Boost higher order functions. Boost higher order functions has a lot of really sophisticated stuff for helping you with doing fancy functional stuff like currying and what have you. But these bread and butter things are suspiciously missing, except for Compose. It's there. Yes, Victor?
Have you thought about submitting your algorithms to BoostHoff?
No, I haven't. But then, like I said, I only heard about BoostHoff last week, so I haven't had time to digest the idea yet. So, takeaway message before we're done. As I said so many times, write functions that use the auto-return type to return lambdas, where the lambdas capture the function parameters and does stuff. And write functions that accesses or modifies your state. There is a talk available in various forms on YouTube by a guy named Klaus Igelberger. The name of the talk is something along the lines of free your functions or something such. Watch it. It matches. It is actually not at all about the things I have talked about today, but it matches perfectly with what I've talked about today. It's the power of freestanding functions, and you can use the functions to communicate with your object and call member functions. So watch Klaus Igelberger's talk about free your functions or something such. I don't remember the exact title. And compose functions, and give the composition names that means things that you can argue with your colleagues about, because that is good. That raises your understanding of your problem. And use functional, if you can. Functional extensions to OptionalT, that is so cool. I forgot to mention, there is another thing that Simon Brand also has, is an expected T and E. Optional is sort of expected T and void. So expected T and E says it either holds a T or it holds an E, where E is considered to be some kind of error information, not just, I could not provide you a T, sorry. It says, I could not provide you a T because E. And then the or else function is called with the E, so you can take different actions depending on what the E is. So that is cool. And like I mentioned, overloads can be a little bit of a pain point, but they are solved by adding another level of interaction. And with that, I'm done. Thank you very much for your attention. So, Victor?
Seeing that using monadic extensions like optional IfThen or else reduces the need for actually extracting the values out of the optionals because I find the syntax very awkward. They use the pointer, smart pointer like syntax for extracting value.
Oh. So the question was, in my experience, using these functional extensions like and then or else, and there are others also, I just gave a very brief intro. Does this reduce the need for obtaining the value because the optional is kind of awkward in that? And my answer is yes, absolutely. You saw it. In my very small example of using them, I didn't call .value or operator star. I didn't have to because I passed the value on in my and then. More questions?
So
Yeah?
you are saying that with an object, the object instead of having having methods, there should be freestanding functions that access either those methods or kind of
Do I mean that you should use naked structs and have free functions that access them instead? No, that is not what I mean. I guess you can do that, but that is pretty much what you do in pure functional programming languages. But I like the idea of information hiding in objects and having member functions. But it's a very good idea to, in addition, write access functions that does things with your object. That is my take on it anyway. Yeah. Other questions? No? All right. Thank you very much.